Hi everyone, welcome back. So in this video, I thought I will continue on the oscillator track. Since in the last video we discussed kind of the analysis and intuition behind cross-coupled oscillators. In this video, let's go ahead and design one using Cadence. So to do that, we'll look at a couple of things first. So I just want to mention one correction from the last video. So when I was doing the optimum NF min versus the current density. At the end, I used Y min. I should have used X min function, which I wrote in the comments down below of that video. So anyway, once you do that, you should see if you go back and open that setup, go back and open the state, you'll see it should actually be JD op should be around 0.1 milliamps per micrometer. So just take note of that. Okay, so we know that JD, the maximum optimum current density in terms of noise figure is 0.1. And in terms of FT, it was, I believe, around 0.3. And in terms of F max, it was around 0.2, right? So, okay, the range should be between 0.2 to 0.3. We know that 0.1 to 0.3, right? The optimum current density. So that's an important kind of rule of thumb to keep in mind, right? For these kind of designs. And one more thing I would like to take a look at is what are the capacitances at the transistor, because we need that value to design the oscillator as we saw, right? So let me just quickly load this state. And then we'll run the simulation once. So that's done. And then I want to say results, no, tools, calculator, operating point. I select this. Actually, no, this is not the way to do it. So I'll say results, print DC operating points, and I want to look at all of these, right? Okay, so if you look at these capacitances, you see about gate capacitance around 3.5 femto. And nothing really is getting beyond 5 femto, right? At max, you get like around 3 to 4 femtofarads. Yeah, cell capacitances. So let's estimate maybe like, the capacitance overall that each branch sees for this oscillator is around like no more than 10 femtofarad, right? So that's a good starting number to keep in mind. So if you go back and look at the design equations, which I had in the previous video, let me pull that up. Okay, so this is just a first pass design based on the equations we had in the last video. So if you go, if you put some numbers in here and actually calculate what the starting value should be, we have, let's say, DC power consumption of 1 milliwatt, VDD 1 volt, and we saw that the threshold voltage, you can also get that from the operating point that we just did, is around 580 millivolts. And let's say the Q of the inductor is around 8. It's a reasonable number at 10 gigahertz. And we want this design to be at 10 gigahertz. And let's say C out, and this should actually be 10 femto, right? That's what we just decided on. It's actually what I used down here. So let's assume it's 10 femto. ISS, because you get it from PDC and VDD, that's 1 milliamp. And RP from this equation should be around 455 ohms to get the swing that we want of this V threshold, right? Then L1 comes from the Q and RP, and that's around 0.905 nanohenry. And the capacitance is around 280 femtofarad for that frequency of 10 gigahertz. And from that, we remove this 10 femtofarad that is like the parasitics, right? It's just an approximate number. This is a first pass design. Let's see how close this gets. So that leaves us with around 270 femtofarads of capacitance that we need. And the WL ratio I've chosen to be 5 micrometers so that the current density in each branch, when each branch is pulling all of this current, 1 milliamp, then at that time, the current density is around 0.2 milliamps per micrometer, right? Because it's 1 divided by 5. Okay, so this is the first pass design. Let's go ahead and make a circuit that has these parameters and see what it oscillates at, what the oscillation behavior is like. So keep in mind that here we've kind of tried to optimize the phase noise for a given power budget, right? That's the design philosophy that we went with. So I've already kind of designed this, put this up, I guess, in a design. I'm not going to go over and show you how to draw this again. Essentially, what I've done is I have my tank here, LC tank, L1, C1, and RP. And then again, L1, C1, RP. I have two VDD nodes here. You can get that from analog lib. I have my one transistor here, another transistor here, and they're cross-coupled, as you can see. And then I put some labels. So to put labels, you can click L, and the ground label is special. It's GND exclamation, and hit enter. And then you can label this node, for example, U for undo. So I've labeled this ground, as you can see here, labeled this body as ground. And then I have a current source at the bottom, as we discussed in the last video. So right now this is ideal. In future videos, we'll make this non-ideal. And I've set the current value here to be ISS, right? So this is also grounded. And here I have basically this defines the VDD voltage, it's VDC. And I've labeled this net as X, sort of this entire thing as X, and this as Y, the two outputs. And I'm also placing a small pulse signal between X and Y to give it some kind of a startup, right? You can also use the noise in the circuit to start up, especially in transient simulation, as we'll see. But it's usually better to start up the oscillator using a small pulse signal. So if I hit Q, you'll see I've set the current to be around 1 milliamp, and it's a very short pulse. The pulse width is only 3 picoseconds. Rise time and fall time is 1 picosecond. So it's a short pulse that we provide just to kickstart the oscillator. It needs some kind of impulse. There's no noise involved. So that's essentially the setup. What I'll do is I will create the ADE from scratch this time, just to give you some idea of what we're doing. Okay. So we said this is 270 femto, C1, it's in channel width, let's say 0.5 micrometers. ISS is 1 milliamp. This should be 0.5 micro. L1 was 0.905 nano. N fingers is 10 fingers, so you get 5 micro. Total N fingers times channel width. RP 455 ohms, and VDC is 1 volt. Okay, I'll create two more parameters here. Edit, and I'll say F naught, which is the frequency that I expect this to oscillate at, which is 10 gigahertz. And I will also create one called del F. So this is the offset frequency at which we're going to calculate the phase noise. So for now, I'll just say 10 kilohertz. Add. Okay. All right. So now that we've created those, let's go ahead and set up some analysis. So I'll do transient analysis over 100 nanoseconds. Make it conservative. So you can set transient noise if you want to help with the startup condition, but we'll do noise simulation separately. So I'm not doing that since we already have a startup with the pulse. Okay. And then I'll also set up HB analysis. So there are two ways to simulate oscillators. Is HB, and there's also periodic steady state. We'll do both and see what the results look like. Typically, periodic steady state is meant for oscillator design, so it's probably more accurate. It's a time domain analysis, whereas HB is frequency domain, and it's meant for sort of in general nonlinear circuits. Maybe we'll cover the way that these two work differently, how they actually work in a different video. But for now, let's just go ahead with setting it up mechanically. Okay, so I'll say, okay, you can decide transient automatically. You can also save the transient result if you want to take a look at it. And I'll say the fundamental frequency is around F naught. So you just have to estimate what the frequency would be, and then it will kind of calculate around that region if there are any frequencies, right? And then the number of harmonics, depending on how nonlinear your oscillations are, your oscillator is, you have to calculate higher harmonics. So here we'll probably have quite a few higher harmonics in the current content. So I'm going to set this to 20. Make it conservative if you like, that makes it more accurate. And then we have to specify that this is an oscillator. Okay, then I'll select the two nodes as X and Y. Click on those. And that should be it. Okay. So we'll also set up periodic steady state. Go up and then say PSS right there. You can leave this blank. Beat frequency, since it's free running, we'll set this to F0. When we do PLL, we'll see what to set this at in the future. And then again, I'll say 20 harmonics. Conservative. You can run transients. Detect steady state. And we'd again specify that this is an oscillator. So I can just select it on the schematic. Okay, that's done. That's pretty much it. And hit OK. All right, and then we also need to set up the noise simulation. So there are two options. You can do P noise or HB noise. I think they both give the same results, so you can pick either one. Even the setup is essentially the same. Even in PSS, there are two options, shooting and harmonic balance. So we are going to use shooting because we set up harmonic balance separately, right? So here you have two options so that you can just quickly toggle between them, basically. But this, I think this harmonic balance and HB is the same. So, okay, so we'll do P noise. So it's saying, okay, the beat frequency is F0, which is correct. The harmonic is the first harmonic, right? And then we want to sweep from, let's say, 10 kilohertz offset to 1 megahertz offset. And we need to make this relative. Okay, the sideband can be maximum sideband. Output should be voltage, and then we'll select the two nodes, X and Y. Okay, and here you want to select all. So AM noise, PM noise, upper sideband, lower sideband. And that should be it. Okay. So we've set up 4 different simulations. We'll compare transient HBPSS in terms of what frequency they estimate. And then we look at the phase noise using P noise. Okay, I think that's pretty much it. We don't really need any of the other ones right now. And maybe in later videos, we'll look at PXF and things like that. So, okay. So that should be enough. We can, I think, run the simulation. So we get 0 errors. That's good. We can close this. And let's look at some results now. So first we look at the transient simulation. One more thing I wanted to do is to save these outputs so we can look at the currents at these outputs. So for voltage, you don't need to save, but for current plotting, you need to save. That's the difference, I guess. So I've saved these two, and let's run the simulation again. Okay. So results, direct plot, main form, transient simulation, voltage. I just want to look at a single node for now. We'll add this to outputs. There we go. Started oscillating. Current. Look at this terminal. Okay, there we go. All right. That's probably enough for now. So I'll call this Vx. And this is Ix. Okay. So let's plot Vx. So we can zoom in by right click and then zoom in. Okay. So we see that this has, center voltage is around VDD, the DC part, and then it swings up and down by about half VTH, right? So we can actually send this to calculator. And I can say peak to peak. And then send this to the ADE. It's around 526, right? And we saw that VTH was around 580. So it's close to VTH. Over the peak to peak is close to VTH, which is what we expect, right? If we wanted to avoid triode region. So that's good. So that has worked well. All right. So from transient, we can do one more thing. We can also plot the VY just to compare them. Yeah. Okay, there we go. So that should plot VY. And I'll label this as VY. Move it up there. And let's compare these two. So you see they're exactly differential, right? Very nice. So as we expect. And they cross exactly at 1. So far so good. All right. So we look at IX and IY also maybe. Like plot main form. I'll say this one. All right. So we've done that. Let me call this IY. Okay. So let's go in and look at the currents. All right. So we see that it looks kind of like a square wave, right? Which is what we expect. Which is very nice. It's first pass design and we already got it, right? So one thing we can do is to see, if I increase the size, does this change? Things like that. You can play with that and see. Essentially, you want to make sure that you don't drive it beyond this. Otherwise, you'll start getting worse noise performance, right? Because we saw that sort of one way to think about that is that the noise figure minimum was at lambda, was when the width was 10, and we are only at 5 right now. Yeah, so you can try different sizes and things like that and see if this gets any better. But essentially, we are driving it to pretty much a square wave. I don't think it'll improve much. So we can quickly try that if you like. So let's increase the number of fingers to like 12 fingers. And then I'll say append. And we'll only plot IX. Right, so you see the shape hasn't really changed much. It's about the same. So we're already kind of driving it as hard as we can. So the current is fully steering right to one side. So you can see it's like 1 milliamp at the peak. So I think 10 fingers is good enough, and we'll see later why that's probably the reason. And we look at the phase noise. Let's go back to 10. I'll close this. And we looked at IX and IY. One more quick thing I want to show you is you can plot even the differential current and voltage. So I can say differential nets, and then I click positive and negative, and that would plot the differential swing. And you can see differential swing is twice as much, right? And it's centered at 0, of course, right? Because the VDD is the same on both sides. And from here, you can get the peak to peak to be more than 1 volt, which is nice. All right. So let's go ahead and estimate the frequency from transient simulation. So maybe I'll delete these to clean things up. Plot it. So one way to do it is to say, okay, you have this. You can say measurements and then say click on it first and then say measurement and spectrum. So you'll see the signal up there. And we want to cut off this beginning part where the startup condition occurs, right? Because you don't want to estimate the spectrum of that part, only the steady state region. So I'll say start time is maybe 10 nanoseconds and stop is 100 nanoseconds. And you can increase this to anything you like. Hit S so that it estimates the start and stop frequency. And then say plot. So that'll give you like a spectrum, right? So that's the spectrum. We can send this to calculator. So you can see that the frequency is very close, 9.9777, right? It's very close to 10 gigahertz. Send to calculator. Let me delete all of these. All right, so now what we want to do is we want to find the peak value of this. So to do that, we will select peak, and then maybe select from, so we select the peak, right? And then we can set this to be from 1 gigahertz to 20 gigahertz, because we know it's between that. And then I'll say, okay, this is going to pick all the peaks basically from in this range, and then say apply. And then I want to get the maximum of this, right? I'm doing it this way because you have another peak at DC, which I don't want it to pick. And there are other ways to do this. You can play around with different approaches if you like. And then I'll say, okay, what is the X value for the maximum of this? And then you can see this should give you the right result, around 9.97 gigahertz. So we'll send this to calculator, ADE outputs. And so that's one way. Another way is to send this to calculator. Actually, not this. So you can actually send this to calculator and then take the DFT. Right? And then you can say 20 times log 10 of the absolute value of this. And that should give us the same result, exactly the same result at the spectrum. Okay, so I'm just showing you that where the spectrum actually comes from. So, and here I've set the value of the DFT again from 10 nano to 100 nano with 4096. I did that before. That's why the default values came up like that. Okay, so that's where the spectrum comes from. This is not the time, although the time domain solution is very accurate. This frequency spectrum is not as accurate because you're using an FFT. So you have frequency bins essentially, and it'll fall into one of the bins. So you have some uncertainty as to where inside the bin the frequency is, right? So this is not like the most accurate frequency that you can get. But anyway, that's one of the frequencies. So here I can say, transient frequency. Okay, so let's look at a different way to get it from transient results. So I'll again plot this. You can say send to calculator, and then you can directly use this frequency function. Sorry, it should only be done once. Okay, and then that'll give you the frequency directly. So that's another way, right? So I cleared that. Send to calculator. Not again. All right. Send it to outputs. Check the value. It looks right. There's another function that you can use. So there's also a freq function, right? This one. And this essentially calculates kind of the instantaneous frequency with time. So let's apply this. And then if you plot this, you'll see, okay, delete that. So you see the frequency is instantaneous for time. So what you should do is you should actually clip this, and then you can take the average value, and that's exactly the frequency function again. So let's look at that. Oh, one mistake I made. Actually, when you calculate this frequency, you need to clip it. So let me show you that. Send to calculator. So before you calculate frequency, you should clip this data. So we'll say clip, and then clip it from 10 nanoseconds to 100 nanoseconds, which is what we did in the spectrum calculation. So once you clip, only then apply this frequency, because you don't want the startup region, right? So let's send this to outputs and then look at the result. It's fine. Okay, very nice. So this is transient frequency 2. Hit OK. And then if we calculate these values again, I don't know why this one is not working. Anyway, so you can go with this result. This is accurate. All right. So from transient, we see it's about 9.99, very close to 10 gigahertz that we designed for, right? But let's look at the result from HBN PSS. So I'll say detect main PSS, and I want to look at the voltage. Let's say single net. I want to look at the spectrum. You can also look at time domain, the peak value in dB, right? And then it'll just say select the net on schematic. We'll select this net. So this is giving you the spectrum now, right? And you see there is like all of these harmonics, right? And the even harmonics are suppressed, whereas the odd harmonics are not, because this is a differential oscillator. We'll cover that maybe in a later video, but a differential oscillator, the even harmonics don't show up, especially if you look at the common mode. But even for a single branch, that's the case. Okay. What we can do is send to calculator and then harmonic frequency function. And we want the first harmonic, apply. Send this to outputs, and we can look at the result here. It's different, right? It's around 10.065. So I'll say this is PSS frequency, and then hit OK. And this is the PSS spectrum. All right. And then the last one is HB. Again, voltage, net, TV, same setup. Click on this, and you see it's a very similar result, right? 10.0658. Slightly different, but very similar. Again, we can send this to calculator and then say harmonic frequency, first harmonic, apply, and then check its result. Close this. And then I'll say this is the HB spectrum. And this is the HB frequency. Okay, so we see we have several different results. Is this again? Oh yeah, it's here. Okay. So we have around 9.99 from transient and 10.065 and 10.0658 from, I thought I changed this. Oh, I changed the expression. That's not right. Anyways, okay. So that should be 10.065. Let me do this again. Oh, let me fix this. I messed up the naming. Okay, so I fixed it now, did that again and got the naming right. So in this case, I would actually trust the PSS result the most, and then close second would be HB and transient the third, just because of the way we extracted the spectrum from the transient result. The transient time domain signal, although I think is the most accurate probably. So if you want to look at time domain results, transient is very accurate. And in case of oscillators, PSS is also very accurate because PSS is actually a time domain solver. It detects the steady state in time domain and then extracts the steady state parameters from the time domain simulation. HB is a frequency domain simulator where it estimates all the different harmonics that can exist in a nonlinear circuit and then matches that with the linear part. We'll go into more depth of these solvers later maybe, but for now, this is how to simulate, right? So far we've looked at, I mean, power consumption is fixed already. We got the right swing, we got the right VDD. I mean, VDD is fixed, sorry. We got the right swing, we got the right current steering, and the current density looks fine. So even the first pass design was very accurate, right? So you can obviously tune this a little bit if you care by tuning the capacitance values. For example, if I make this 268 femto or 272 femto, maybe that would give me slightly better results. It's closer, maybe 275 femto. Depends on how much you care about this. Right? Okay, so that has changed a lot now, actually. So let's go back to 270 femto. You can also play with other results. We'll do that. So the next thing you want to look at is the phase noise performance. So I can say, go back up here, say P noise, phase modulation. So if you want to look at the phase part, you can also look at the amplitude part, but you will see actually this is much lower. And then click on phase noise and then just say plot. And this is the phase noise spectrum from 10 kilohertz to 1 megahertz offset. So for example, if you look at 100 kilohertz offset, it is around minus 83 dBc per hertz, right? So if I look at, for example, the amplitude modulation part, let's say dBc per hertz, single sideband, and then plot. See, it's much lower, right? And when we talked about the phase noise in the ISF model video, I showed that we saw that amplitude modulation part of the phase noise is corrected by the limit cycle, and that's why that component is very low, whereas the phase modulation part is much higher, right? Much more significant. So that's how you plot the phase noise essentially. So let me delete this, and I'll call this phase noise. Okay. So now what we would like to do is to plot the phase noise figure of merit, or to find the phase noise figure of merit. And I have a definition here for you as to what that's defined as. So it's defined as the phase noise at some offset frequency delta f minus 20 log f naught, which is the center frequency or the oscillation frequency divided by that delta f plus this power, right? So the reason it's kind of defined like this is because the 1 over f square region of the phase noise, you want this phase noise figure of merit to be independent of that, right? So for example, if we know that in the 1 over f square region, this drops by 20 dB per decade. And if you increase this by a factor of 10, that's 1 decade, then this should also drop by 20 dB, right? So this factor remains constant, and we'll see that actually for different offset frequencies. In the 1 over f cube regions, that's not true, because this drops by 1 over f cube by 30 dB per decade, whereas this only changes by 20 dB per decade, right? But this is defined to be sort of invariant in the f square part of the phase noise. If you don't know what I'm talking about, you should watch the phase noise model video that I made using ISF model, the phase noise video. And you also want to kind of include the power consumption inside this, because of course phase noise scales with power consumption. So if you consume more power, this performance should go up. So that's why that's also included. And P is usually written in milliwatts, right? So let's code this up into Cadence and see what that looks like. Okay, so the first term is the phase noise at some offset. So we essentially take this function, send it to not to ADE. So I'll send this to the calculator, and I want to evaluate this at what's the value at an offset of del F, right? And that's the delta that we set up there in the variables, and then say apply. And the next term is minus 20 log F naught over delta F. So what is F naught? We already have it here. So I can extract it, let's say, from the PSS frequency. So I'll use this expression, copy this. I'll say minus 20 times log 10 of this divided by del F. And when we say del F, we want it to be a variable, right? Del F. Okay, that's good. So that's the second term. And then the third term is plus 10 log power in milliwatts, right? Plus 10 times log 10 of, and we know that we already set the power in milliwatts to be 1 milliwatt. So I'll just say 1. You can also make that a variable if you like. So let's evaluate this. And of course, there's some issue with it. Okay, this should be. There we go. So that's the phase noise figure of merit. Let's go back and we'll send this to the results. So I'll label this as phase noise form. All right, So if you look at that results around minus 183, that's a good number actually. It's not that bad. Of course, the first pass design, and we've also used some ideal components for these inductors and so on. In future videos, we'll kind of see how to make this tail current source more realistic. We haven't done any kind of phase noise improvement to this architecture that we started with. So as a first pass design, that's a good phase noise. So one last thing I want to look at is the phase noise as a function, as phase noise figure of merit as a function of this del F. Right, so let's look at that. So we'll sweep this from 10K to 1 meg. I'll make this logarithmic and let's do 21 steps. And I don't want to plot all these results. We'll just plot that. Okay, so let's see what this looks like. It's going to take a few seconds. Okay, so that finished running, and you can see it's fairly stable even at, at the 1 over f cube region, which is somewhere here. We'll actually see how to extract which region is 1 over f cube, which region is 1 over f squared, but this is one way to look at it. So I said it's going to be more or less constant in the 1 over f square region, and we see that happening here, right? So this is kind of the number that you would kind of report if you're reporting the phase noise figure of merit. You shouldn't go beyond the 1 over f square region where it becomes flat, because then again, it's not the right value, right? So you want to report it in the region where it's sort of constant. So that pretty much concludes what I wanted to show you today in this video. So we looked at how to set up this simulation that we started with. We did the analytical calculation based on Behzad Razavi's sort of design procedure, more or less the same as what he proposes. And we looked at, different ways to simulate it using transient, HB, PSS, and P-noise. And we said, okay, PSS is probably the most accurate way to do this because free running oscillator that has some periodic steady state. And then we looked at how to extract the frequency of oscillation, the power at each node, the differential voltage and current. And we saw that the swing looks pretty much correct. And finally, we looked at the phase noise and how to extract the phase noise figure of merit, right? So you can obviously play around with these values here and see how it changes the phase noise figure of merit. So we can make this, for example, 5 fingers. And so form went down, right? Because I think, yeah, essentially what we started with is the design should be this exact result, or the values here were chosen such that we get the best phase noise performance for a given power consumption. So 10 seems to be somewhat optimal, close to optimal. And you can obviously play around with other values as well. Number of fingers should, but one more thing, the number of fingers should usually be higher than 5 or 6. So I typically set it to 10, but again, this is sort of a rule of thumb, right? You can change this if you like. All right, so that pretty much concludes what we have done here. I would like to, in the next video, maybe look at how to make this more realistic using current mirrors and how to design the current mirror correctly. And then we'll also make this realistic. We'll probably do the layout for these transistors and combine all of this into one oscillator that is actually more realistic at 10 gigahertz. So once we finish all that at 10 gigahertz, then we'll move on to doing millimeter wave, let's say 100 gigahertz oscillator, right? And we'll see where to go from there. I'll also show you how to simulate the ISF function using an impulse current source. So the time domain ISF simulation for both stationary and cyclostationary noise sources. Okay, so a lot of exciting stuff coming up. Hopefully this is a nice first circuit design, since this is like the first actual circuit design that we did. Hopefully it's like somewhat interesting. So if you have any questions, if you find any mistakes or comments or suggestions, please leave them in the comments below, and I'll see you in the next one. Thank you.